Hey fellow nerds, today we are going to discuss common base amplifier. We will be covering its small signal hybrid pi model, voltage gain, input impedance, output impedance, and biasing. Let us start by understanding what is the common base configuration. A basic common base BJT amplifier circuit looks like this. You can see that the output is still taken from the collector, but the input is given at the emitter. Let's figure out its small signal model. For that, first I'll take the small signal hybrid pi model of a BJT. Let us show the input. It is supposed to be given at the emitter. Now, output is taken at the collector. We also have a resistor RC at the collector. In the small signal model, it will go to the AC ground. At the base, we have the bias V0. But in the small signal model, it will be shorted. So base will be directly going to the AC ground. So this is the small signal model of a basic common base amplifier that we're going to use in this video. Let us use it to find the voltage gain. Let us start by applying Kirchhoff's voltage law in the input loop. This is the input loop. I'll start from the ground. I have my R pi. There is the emitter. There is my input and I go back to the AC ground. There are two voltage drops. One is V pi, that is across R pi. The other is our input voltage V in. If I go clockwise, V pi is from positive to negative. V in is also from positive to negative. So they are in the same direction, which means I can write V pi plus V input is equal to 0 according to Kirchhoff's voltage law. Now that means V pi is the negative of V input. Let it be there. Let us apply Kirchhoff's current law at the collector. This is the collector node. I can see two currents. One will be the current that will flow through RC. The other will be the current that we have over here, GMV pi. Let's take the current flowing through RC to be I. Both currents are going out of the node. According to Kirchhoff's current law, their sum should be 0. GMV pi plus I should be equal to 0, which means I is a negative of GMV pi. Now, if you take a look at RC, you can see the potential across it is equal to the output voltage. Current through it is I. So using Ohm's law, we can write V output is IRC. But I is minus GMV pi. So we can write V output is minus GMV pi RC. Again, V pi is minus V in. So we can write V out this way. Negative and negative will get cancelled and we get V output is simply GMV in RC. What we want is the voltage gain, which is V output divided by V input. From this equation, we can easily write it. It is GMRC. The voltage gain is GMRC. This is exactly the same as the common emitter amplifier, except it is positive. In common emitter amplifier, the gain was negative GMRC. Now we have positive GMRC. So we can say when it comes to the common emitter amplifier, the phase difference between the output and input is 180 degree because of the negative sign. Here it is 0 degree because there is no negative sign. Now let's try to find the input impedance of the circuit. For that, the first thing we have to do is remove all the independent sources in the small signal model. The only independent source we have here is V input. So we have to remove it. If we remove V input, that means if the voltage between this point and this point should become 0, that means emitter will be directly grounded. Now the next thing we have to do is apply a potential Vx at the input. In the common base configuration, input is given at the emitter. So we have to apply Vx at the emitter and find its relation with Ix, which will be the current that flows over here. Let us start by applying Kirchhoff's voltage law at the input loop. This is our input loop. I'll start from the ground. There is R pi. I reach the emitter. I have Vx and I go back to the ground. There are two potential drops, V pi and Vx. V pi is from positive to negative. Vx is also from positive to negative. So according to Kirchhoff's voltage law, V pi plus Vx will be equal to 0, which means V pi will be negative of Vx. Now let's apply Kirchhoff's current law at the emitter. I can see three currents at the emitter node. GM pi is coming into the node. Ix is also coming into the node. Another current will flow in this direction into the node. What will be this current? It is the current that will flow through R pi. R pi has a potential V pi across it. Its resistance is R pi. So this current is going to be V pi divided by R pi according to Ohm's law. Now, according to Kirchhoff's current law, the sum of all these currents should be 0. V pi by R pi plus Ix plus GM pi should be equal to 0. But V pi is minus Vx. So we get minus Vx by R pi plus Ix minus GM is equal to 0. Or we can write Vx by R pi plus GM is equal to Ix. Vx by R pi plus GM can be written as Vx multiplied by 1 by R pi plus Gm. What we want is Vx by Ix. From this equation, we can easily write it. Vx by Ix is 1 by R pi plus Gm. Now, we know beta is Gm R pi. From here, we can write 1 by R pi is Gm by beta. So, in the denominator, we get Gm by beta plus Gm. This can be written as Gm multiplied by 1 by beta plus 1. Now, 1 by beta plus 1 is beta plus 1 divided by beta. Now, this is something we have done multiple times. Beta is supposed to be a large number. For example, if you take beta is 125, then beta plus 1 by beta is 126 divided by 125, which is approximately equal to 1. So, this whole thing can be approximated to just 1 by Gm multiplied by 1, which is 1 by Gm. So we can say Vx by Ix is approximately equal to 1 by Gm. Vx by Ix gives us our input impedance. So the input impedance of this circuit is 1 by Gm. Let's take an example and give some values. Assume the collector current is 1 milliampere. We know Gm is Ic by Vt. Our input resistance is 1 by Gm, so it will be Vt by Ic. Vt is the thermal voltage, which is 26 millivolt. Ic, as we have taken here, is 1 milliampere. So the input resistance will be 26 ohm, which is very low. So we can say for common base configuration, the input impedance is relatively low. But when we started the discussion on amplifiers, we said a higher input impedance is desirable. But here we got an amplifier that has a relatively low input impedance. So my question is an amplifier with a low input impedance useful? Actually, there are situations where we need amplifiers with lesser input impedance. Let us see an example. We know that according to maximum power transfer theorem, maximum power is transferred from the source to the load if resistance of the source is equal to the resistance of the load. So when it comes to a circuit like ours, we can say for maximum power transfer, load impedance should match the source impedance. This is called impedance matching. As an example, assume we have a transmission line through which the input signal is being transmitted. Transmission lines usually have less impedance. Now, for maximum power to be transmitted from the transmission line to our amplifier, input impedance of the amplifier should match with the impedance of the transmission line. We need the input impedance of our amplifier to be 50 ohm as well, which is relatively low. So we can say amplifiers with low input resistance are useful to provide impedance matching between modules that are in a cascade and the transmission lines that are between them. Now, let us also include the resistance of the source and see how it affects our voltage gain. You can see that in the circuit, I have also added Rs, which is the resistance of the source. So in the small signal model, we'll have Rs over here. Here to find the new voltage gain, I am going to use a trick. We already saw that this much of this model is equivalent to a resistance 1 by Gm. So I can model this whole thing into a much simpler version like this. V input, I have it over here. In series to V input, I have Rs. In the new model also, I have the same. Over here, I have marked the point as X and potential is Vx. Over here also, I have Vx. And the rest of the circuit is equivalent to a resistance of 1 by Gm. I modeled it with a resistor of 1 by Gm. Now, from this, I can easily find out what will be the potential that I get at this point. We only have to use simple voltage division. V input is being divided between Rs and 1 by Gm. And whatever is dropped across 1 by Gm will be equal to Vx. So we can write Vx is 1 by Gm divided by Rs plus 1 by Gm multiplied by V input. If we multiply the numerator and the denominator with Gm, we get Vx is V in divided by 1 plus Gm Rs. Now previously we learned without the source resistance being considered, gain is GMRC. That is output voltage divided by whatever is the voltage we actually get at the emitter is GMRC, which is Vx. So here we can write V out by Vx will be GMRC. But we know how to write Vx in terms of V input. Using that, we can write V output divided by V in by 1 plus GMRS is GMRC. What we want is V output divided by V input. So let's take this much to the other side of the equation. That gives us V out by V in is GMRC divided by 1 plus GMRS. Let's divide the numerator and the denominator with GM. That gives us RC divided by 1 by GM plus RS. So the gain is RC by 1 by GM plus RS. Now, what if RS is 0? If RS is 0, this simply becomes RC by 1 by GM, which is GM RC. Makes sense because we have already seen when the source resistance is not included, gain is GMRC. One more thing we can do is, if we make sure Rs is very much greater than 1 by Gm, then in the denominator 1 by Gm plus Rs can be approximated to just Rs. In that case, the gain will be approximately Rc by Rs. This is actually analogous to when we had the emitter resistor in the common emitter amplifier. In common emitter amplifier with emitter degeneration, we saw gain is negative Rc divided by 1 by Gm plus Re. There also we said that if Re is very much greater than 1 by Gm, then the gain is approximately minus Rc by Re. Let us now include a base resistor and find the voltage gain. In the circuit diagram, you can see I have added Rb over here. I still have Rs, I haven't removed it. So the small signal model will look like this. Rs is over here at the emitter, Rb is over here at the base. Let us start by applying Kirchhoff's current law at the collector. I can see two currents at the collector node. One is GMV pi that is going out of the node. The other one is whatever is the current that flows through RC. Now for RC, potential across it is V out. Its resistance is RC, so this current will be V out by RC. According to Kirchhoff's current law, the sum should be equal to 0. GMV pi plus V out by RC should be equal to 0. Or we can write GMV pi is equal to negative of V out by RC. That gives us an expression for V pi. V pi is minus V out divided by GMRC. Let it be there. Let us find an expression for the base current. That means the current that will flow like this. It is the current that flows through R pi who has a potential V pi across it. So base current is going to be V pi by R pi. But V pi is minus V out by GMRC. So we can write base current is minus V out by GMRC divided by R pi. But what is GM multiplied by R pi? It is beta. So we can write base current is minus V out divided by beta RC because GM R pi is beta. Now let's take the point over here, call it X. The potential at X will be Vx. Consider Rb and R pi that are in series. They have a potential Vx on one side and 0 on the other side. There is a current that flows through them in this direction, the base current Ib. Now Ib is V pi by R pi. V pi has positive potential here and negative potential here. So the direction of Ib is like this. So let us mark Ib over here in this direction. Ib is flowing through Rb and R pi from 0 to Vx. If Ib is flowing in this direction, that must mean potential here is higher than the potential here. So using Ohm's law, we can write Ib is 0 minus Vx divided by Rb plus R pi. And from there we can write Vx is minus Ib multiplied by Rb plus R pi. But Ib is minus V out by beta Rc. So we can write Vx is plus V out by beta Rc multiplied by Rb plus R pi. The negative we have over here and the negative here got cancelled and it became positive. Let us now apply Kirchhoff's current law at the emitter. This is the emitter node. I can see three currents. One is GMV pi coming into the node. The other is the base current V pi by R pi coming into the node. The third one is the emitter current. I am taking its direction like this. Here V pi by R pi is coming into the node. GMV pi is coming into the node. IE is going out of the node. So according to Kirchhoff's current law, V pi by R pi plus GMV pi should be equal to IE. Now let's try to find an expression for IE. IE is the current that will be flowing through RS. RS has a potential Vx here and V in here. IE will be flowing like this. So according to Ohm's law, IE will be Vx minus V in divided by RS. Let us replace IE in this equation with Vx minus V in divided by RS. On the left hand side, we have V pi by R pi plus GM V pi. That can be written as 1 by R pi plus GM multiplied by V pi. Again, we have another expression for V pi. It is minus V out by GM RC. So the left hand side of the equation becomes 1 by R pi plus GM multiplied by minus V out by GM RC. On the right hand side, we have Vx. But we have another expression for Vx. It is V out by beta Rc multiplied by Rb plus R pi. If we replace Vx with that, this is what we get. Here we have 1 by R pi plus Gm. I am going to add them and write 1 plus Gm R pi divided by R pi. Also, I'll take the Rs over here to the left hand side. Then the equation will become like this. Now we have a GM R pi over here. We have another one in the denominator. GM R pi is beta. So we can replace it by beta. The equation becomes like this. 1 plus GM R pi becomes 1 by pi. 1 plus GM R pi becomes 1 plus beta. GM R pi becomes beta. RC is here. RS is here. Negative is here. V out is here. Now on the left hand side we have V out multiplied by this whole thing. On the right hand side we have V out multiplied by this whole thing. Let us put them together on one side of the equation and keep V input on the other side. This is what we get. 1 plus beta multiplied by Rs divided by beta Rc V out plus V out multiplied by RB plus R pi divided by beta RC. From both these terms, let us take V out as common, like this. Now, for both these terms, denominator is the same, so we can combine them and write it like this. So we get V output multiplied by 1 plus beta times Rs plus Rb plus R pi divided by beta Rc is equal to V input. What we want is the voltage gain, which is V output by V input. So from this equation, we get V output by V input is beta Rc divided by 1 plus beta Rs plus Rb plus R pi. Let's divide the numerator and the denominator with 1 plus beta. Then on the numerator, we have beta Rc by 1 plus beta. On the denominator, we have Rs plus Rb by 1 plus beta plus R pi by 1 plus beta. Let's make some approximations. We know beta is a larger value, so beta is approximately equal to beta plus 1. So here we have beta divided by 1 plus beta, that will be approximately equal to 1. Also, here we have R pi by 1 plus beta. 1 plus beta is approximately equal to beta itself. So R pi by 1 plus beta can be approximated to R pi by beta. But R pi by beta is 1 by gm. So this term can be replaced by 1 by gm. That gives us Rc divided by Rs plus Rb by 1 plus beta plus 1 by gm. These are the two approximations we made. Beta divided by 1 plus beta is approximately 1. And R pi by 1 plus beta is approximately R pi by beta, which is equal to 1 by gm. So the voltage gain is Rc divided by 1 by gm plus Rs plus Rb by 1 plus beta. What if Rs and Rb are 0? Which means we are not considering the source resistance and there is no base resistor. In that case, Rs and Rb by 1 plus beta will become 0 and the gain will go back to GMRC. So in general, we can say the gain is the impedance at the collector divided by 1 by Gm plus the impedance at the emitter plus impedance at the base divided by 1 plus beta. Now let's find the input impedance when the base resistor is included. In the circuit diagram, you can see Rb over here. Rs has been removed. So the small signal model will look like this. To get the input impedance, the first thing we have to do is switch off all the independent sources. We have one independent source which is V input. If I switch it off, emitter will be directly grounded. Now to get the input impedance, we have to add a potential Vx at the input which is at the emitter itself and find its relation with the current Ix that will be flowing over here. Consider the input loop. I mean this one. From ground, there is Rb, there is R pi. We reach the emitter, then there is Vx and back to ground. Here Vx is connected across the series combination of Rb and R pi, like this. So to get the potential that is dropped across R pi, all I have to do is use voltage division. Vx will be divided between R pi and Rb. So the potential dropped across R pi will be Vx divided by Rb plus R pi multiplied by R pi. Now potential across R pi, we are calling it V pi. So is this equal to V pi? Here is something that we have to be very careful about. Vx has positive potential here and negative here. So it is giving positive potential on this side of R pi. R pi gets positive potential here and negative potential here from Vx. But we have defined V pi with negative here and positive here. So V pi is not equal to the potential drop across R pi. It is the negative of the potential drop across R pi. So we can write V pi is the negative of R pi by R pi plus Rb multiplied by Vx. Let's write this down. Let us now apply Kirchhoff's current law at the emitter. Obviously, there are three currents. One is Ix flowing into the node. GM V pi is the next one also into the node. The third one will be the current that flows through R pi that is also coming into the node. R pi has a potential V pi across it, so this current is going to be V pi by R pi. According to Kirchhoff's current law, the sum of the three currents should be equal to 0. V pi by R pi plus Gm V pi plus Ix is equal to 0. Here we have V pi by R pi plus Gm V pi. It can be written as 1 by R pi plus Gm multiplied by V pi. But V pi is this much. Using both these ideas, we can write the expression like this. 1 by R pi plus Gm multiplied by V pi, which is this much, plus Ix is equal to 0. Again, 1 by R pi plus Gm can be written as 1 plus Gm R pi divided by R pi. That gives us Gm R pi, which can be replaced by beta. We have R pi here, that can be cancelled. Then the equation becomes like this. R pi and R pi got cancelled. 1 plus Gm R pi, I've written it as 1 plus beta. R pi plus Rb is still here. Vx is here. Ix is here. There was a negative here, but I took Ix to the other side of the equation, so it got removed. Now what we want is Vx by Ix, which is very obvious from here. It is R pi plus Rb divided by 1 plus beta. We can also write it as R pi by beta plus 1 plus Rb by beta plus 1. R pi by beta plus 1 is approximately equal to R pi by beta. And this is approximately equal to 1 by Gm. So we can say Vx by Ix is approximately 1 by Gm plus Rb by beta plus 1. The input impedance is 1 by Gm plus Rb by beta plus 1. Again, what if Rb is 0? If Rb is 0, this term will be gone and input impedance will go back to 1 by Gm. Now this result is kind of analogous to when the common emitter amplifier had a resistor at its emitter. In that case, the input impedance was R pi plus Re multiplied by beta plus 1. Let us see what will be the input impedance if the resistance of the source is also included. I have added Rs in the circuit. In the small signal model also we have Rs. This is actually pretty simple to find out because we already found the input impedance when Rs is not included. According to what we learned, this much of the circuit model is equivalent to a resistance of 1 by Gm plus Rb by beta plus 1. So we can model this entire thing in a much simpler way like this. There is Vx over here. Rs is to be connected in series with Vx. Rs is connected in series with Vx. Ix is the current that will flow through Rs. Here also Ix is the current that will be flowing through Rs. Now the rest of the circuit model is modeled as a single resistor whose resistance is 1 by Gm plus Rb by beta plus 1. Now from here, what will be the new Vx by Ix? These two resistors are in series. So the new Vx by Ix will be Rs plus 1 by Gm plus Rb by beta plus 1. Let us now move on to the output impedance. Early voltage is less than infinity, which means early effect has to be considered. So in the small signal model, R0 will be included. The first thing to do is switch off all the independent sources. The only independent source we have is the input voltage. If I switch it off, the emitter will be directly grounded. Now, what we want is the output impedance. So we have to add a potential Vx at the output and find its relation with Ix, which will be the current that will flow in this direction. We have R0 and Rc in parallel. To keep it simple, let us model them as one single resistor whose resistances are not parallel to Rc. Let us also take the current flowing through these to be I. Now, the first and the most important thing you can see is this. R pi is shorted. Its both ends go to the ground. That means potential across R pi is 0. V pi is 0. If V pi is 0, then Gm V pi is 0. That means no current is flowing in this branch. All of Ix is flowing through R0 parallel to RC, which means I is simply equal to Ix. Let us write this down. V pi is 0, so GM V pi is 0. That makes I equal to Ix. Now Vx is the potential that drops across R0 parallel to RC. So using Ohm's law, we can write Vx is I multiplied by R0 parallel to RC. But I is equal to Ix, so we get Vx is Ix multiplied by R0 parallel to RC. That gives us Vx by Ix is simply R0 parallel to RC, which will be our output impedance. R0 parallel to RC is our output impedance when the early voltage is finite. What if early voltage is infinite and we don't have to include early effect? In that case, R0 will not be there, which means our output will simply be equal to RC, just like the common emitter stage. There is another interesting thing you can see over here. The input impedance was 1 by GM. Output impedance is RC. Gain is GMRC. That means if you divide the output impedance with the input impedance, you get the gain. Let us move on to the current gain of a common base amplifier. Current gain is the ratio of the output current to the input current. Here, output is taken at the collector and input is given at the emitter. So, output current is the collector current, input current is the emitter current. So, current gain is IC divided by IE. We call this alpha. We know IC is approximately equal to IE. So IC by IE will be approximately 1. Let's try to find a relation between alpha and the current gain in common emitter amplifier beta. Alpha is IC by IE, but IC can be written as beta IB. IE is IB plus IC, so we can write IB plus beta IB. Then we get alpha as beta IB divided by IB plus beta IB. We can cancel IB from the numerator and denominator and we get alpha is beta divided by beta plus 1. Let us now move on to the bias design. Before we do anything, let us add AC coupling. That means I'll be giving the input through a coupling capacitor and taking the output through a coupling capacitor. We know that capacitors only pass AC currents and voltages through them. They will block DC current and DC voltage. Assume that we have applied V0 as the biasing. V0 will create a DC collector current. It flows like this through RC, reaches the collector, reaches the emitter, but after that it will not be able to pass through the capacitor because it is DC. That is going to be a problem. So we can say there is no DC path for the emitter current IE. Our bias current will be 0. We know the transconductance is bias current divided by thermal voltage. If bias current is 0, then transconductance is also 0. Gain of the amplifier is GMRC. If GM is 0, that means the circuit is not amplifying. Whatever circuit we have here is not going to work. So we have to do something. Let us try this. We will ground the emitter so that the bias current can flow to the ground like this. Now, will this work or do we still have a problem? Our V input is over here and it is AC. We know for an AC signal, capacitor acts as a short circuit. So basically, V input is being shorted over here. Both the terminals are directly connected to the ground. Grounding the emitter shorts the input. So the effective input our circuit gets is 0. If input is 0, output is also 0, which means again there is no amplification. This is also not going to work. Let's try something else. We'll add a resistor at the emitter. Now the bias current can flow to the ground through a resistor. And since there is a resistor over here, V input is not being shorted. The resistor RE provides a path for the bias current. Let us see how adding a resistor at the emitter affects our input impedance and the gain. For that, we need the small signal model. In the small signal model, we only have AC signals. Assuming their frequencies are in the mid frequency band, we can short all the coupling capacitors. Then RE will be over here in parallel with V input. To find the input impedance, the first thing we have to do is switch off all the independent sources. The only independent source we have is the input. If I switch it off, the emitter will be connected to the ground. Now we have to connect Vx at the input, which is over here, and find its relation with Ix, which will be the current flowing over here. Let us find Vx by Ix using a trick. Assume we don't have Re over here. We have already found the input impedance in that case. The rest of the circuit model has an input impedance 1 by Gm. So without considering Re, the circuit model can be simplified like this. We have Vx, Ix is the current that is flowing over here, and the rest of the circuit is modeled as a single resistor whose resistance is 1 by Gm. Now, if we want to include Re is basically connected in parallel to Vx. So to get the equivalent circuit model for this whole thing including Re, all I have to do is add Re in parallel to Vx. From the simplified circuit model, we can easily say what is the new input impedance. It is 1 by Gm parallel to Re. So the input impedance is Re parallel to 1 by Gm, which is Re multiplied by 1 by Gm divided by Re plus 1 by Gm. Now, when two resistors are in parallel to each other, the equivalent resistance is always going to be less than the smallest one. Without Re, our input impedance was 1 by Gm. Now we have Re parallel to 1 by Gm. So the presence of Re is going to decrease the input impedance. But if Re is very much larger than 1 by Gm, then in the denominator, Re plus 1 by Gm will be approximated to just Re. So we get Re by Gm divided by just Re. Then Re and Re will get cancelled and the equivalent resistance will approximately be equal to 1 by Gm itself. So we can design the circuit such that Re is very much greater than 1 by Gm. So the input impedance is still 1 by Gm. If we take Re to be very much greater than 1 by Gm, that means Re is very much greater than Vt by Ic because Gm is Ic by Vt. Taking Ic to this side of the relation, we can write ICRE must be very much greater than the thermal voltage. But what is ICRE? Re is the resistor we have over here. Current flowing through it is IE, but IE is obviously almost equal to IC. So we can say current flowing through Re is IC. That means ICRE is the potential drop across Re. So the condition we have is actually VRE must be very much greater than the thermal voltage. So that problem is solved. Now, instead of adding V naught directly at the base for biasing, let us try using a voltage divider. I have connected R1 over here and R2 over here. I am calling the current passing through R1 as I1. Now, I1 passes through R1 like this, and some part of it will go into the base. The rest will pass through R2. But for proper voltage division, I want almost all of the current I1 to pass through R2. That is possible if IB is very much lesser when compared with I1. So we have to design the circuit such that I1 is very much greater than IB. So we can say almost all of I1 will pass through R2. So the current through R2 is also taken to be I1. Then we can make sure that V0, the potential that we get at the base, will be approximately R1 by R1 plus R2 multiplied by VCC. The voltage division is perfect. We can even use the Thevenin equivalent of R1 and R2 just like we did in the common emitter stage. Their Thevenin equivalent will be R1 parallel to R2 and it will appear in series with the base. In that case, we can redraw the circuit like this. The voltage divider circuit is replaced by a VTH, the Thevenin voltage, and RTH, the Thevenin resistance. RTH will be R1 parallel to R2. So basically, adding a voltage divider bias gives us an equivalent resistance at the base. But previously, when we derived the voltage gain, when there was a base resistance, we saw that the base resistor is decreasing the voltage gain. Obviously, we do not want our voltage divider circuit to affect our voltage gain. To make sure that doesn't happen, this is what we're going to do. We will add a bypass capacitor and we'll be adding it over here in parallel with R2. Since it is connected at the base, I'll call it CB. Just like any other capacitor, CB is going to act as a short circuit for AC signals and open circuit for DC signals. Now, to understand how the bypass capacitor helps us make sure that the voltage divider circuit does not affect our voltage gain, let us take the small signal model. It will look like this. R2 is connected between the base and the ground. I have shown it over here. R1 is connected between the base and the AC ground. So it is also over here. In the small signal model, it is parallel to R2. Bypass capacitor is also between the base and the ground. So in the small signal model, it will be in parallel with R1 and R2. I have already shorted the two coupling capacitors. Now CB is also going to be shorted because we only have AC signals in the small signal model. When we short CB, you can see that R1 has both its terminals connected to the ground. R2 also has both its terminals connected to the ground. Basically, both R1 and R2 gets shorted. So we can just remove both these resistors from the circuit model and show that base is directly connected to the ground. The simplified version of the small signal model will be like this. Therefore, we can say that by adding the bypass capacitor, R1 and R2 get shorted in the small signal model and they do not affect the voltage gain anymore. Let us now calculate the voltage gain of this circuit. I have also included RS, the source resistance. The first thing we need is the small signal model. It will look like this. Since the bypass capacitor will short R1 and R2, base will be directly connected to the ground. Both the coupling capacitors are also shorted. So at the emitter, we'll have RS in series with the input. There is RE in parallel to it. Now I have marked the point over here as X. So the potential there is Vx. If you take a look at R pi, at one end it has zero potential. At the other end it has Vx potential. So the potential across R pi is actually Vx minus 0. But potential across R pi is also V pi. For V pi we have taken positive here and negative here. So Vx is on the negative end, which means we can write Vx is actually negative of V pi. Now we need an expression for Vx. For that, let us make a simplified model of the small signal model. We have V input to which we have Rs in series. From Rs, we have Re that goes back to the ground. We have already found the input impedance of the rest of the circuit model. It is 1 by Gm. So we can model it as a single resistor whose resistance is 1 by Gm, like this. Now this is a simplified version of the same small signal model. Vx is whatever potential we get over here. We can actually make it more simplified. 1 by Gm and Re are in parallel, so we can replace them by one single resistor whose resistance is 1 by Gm parallel to Re. Now this is the most important thing. Remember when we started the discussion on bias design, we said to make sure that Re does not affect our input impedance, we have to take Re to be very much greater than 1 by Gm so that the input impedance, which is Re parallel to 1 by Gm, will be approximately equal to 1 by Gm itself. So over here in this circuit, 1 by Gm parallel to Re can be approximated to just 1 by Gm because we have already taken Re to be very much greater than 1 by Gm. Now let's use voltage division to write Vx in terms of Vin. Vin gets divided between Rs and 1 by Gm, out of which whatever drops on 1 by Gm is going to be equal to Vx. So Vx is 1 by Gm divided by Rs plus 1 by Gm multiplied by V input. Now let us see the output node, that means the collector node. There are two currents. One is Gm V pi in this direction. The other is whatever is the current flowing through Rc. Now Rc has a potential V out across it. So the current flowing through Rc will be V out by Rc. According to Kirchhoff's current law, the sum of these two currents should be equal to 0. Gm V pi plus V out by Rc should be equal to 0, or we can write Gm V pi is equal to minus V out by Rc. So we get the current that is flowing through Rc is actually minus Gm V pi. Then we can say the potential across Rc is minus Gm V pi multiplied by Rc according to Ohm's law. But potential across Rc is V output. So V output is minus Gm V pi Rc. Now we already found out V pi is minus Vx. So minus V pi over here can be replaced with just Vx. So V output is Gm Vx Rc. Again, Vx is 1 by Gm divided by Rs plus 1 by Gm multiplied by V input. Let us replace Vx over here with that. We have a Gm and a 1 by Gm. They get cancelled. Then we can write V out by V in is just Rc by Rs plus 1 by Gm. This is our voltage gain. This is the same as what we saw before with the source resistance. Now what if the source resistance is 0? Then in the equation Rs will be 0 and gain will become Rs divided by just 1 by Gm, which is simply GMRC, our original voltage gain. So by adding the bypass capacitor, we can make sure our voltage gain is still the same even after including the voltage divider bias. So that's all about it for today. See you in the next video. And please don't forget to subscribe.